The problem we got with shielded metal arc welding is productivity. The reason why is because SMAW is a manual process where the consumable electrode is constantly being replaced once consumed. Also, since the SMAW process has a flux coating, when reacted with the atmosphere, it produces lag, which needs removal as well. So if you need more details about SMAW, you can check out the video right here in the top right corner of your screen. I discussed there also the different electrode nomenclature and uses for SMAW. GMAW consists of a welding gun, the machine itself connected to the power source, the wire spool, and feeding machine connected to the gun. Now this reel, as you can see attached to the wire feeder, contains spools of wire meters and meters long, a shielding gas container, and mixer. Now this reel basically will allow the welder to have spools of wire, filler wire that will allow him to weld in a continuous and productive manner without any need for the replacement of the electrode, unlike SMAW. GMAW addresses the issue of productivity as it is a semi-automatic process. Sometimes it can also be used as a mechanized process, which is very good for robotic welding. GMAW is normally a semi-automatic process because of the wire feeding process. Because it's automatic, the wire feeding process is automatic. GMAW also has an external source of shielding gas such as argon, CO2, and oxygen. Since the wires have deoxidizers, as you can see here, and no flux, GMAW produces little to no slag as compared with SMAW electrodes, which has a flux coating. As you can see here, the electrodes has a flux coating for SMAW. Now, let's discuss the welding gun. The welding gun consists of a connection to the shielding gas, as you can see here. The shielding gas protects the weld from atmospheric gases such as hydrogen and helps in the ionization of the weld, meaning keeping the weld arc stable. Sometimes, for higher heat input machines, cooling water is also attached. This welding gun is also attached to the wire feeder, enabling a semi-automatic process which improves productivity, as I've mentioned earlier in the general diagram. Now, since GMAW has all these intricacies and because of the shielding gas, GMAW is best used for indoor welding to prevent contamination of the weld. It can also be used outdoors, but proper protection against atmospheric gases, such as barriers, must be installed. Because of the atmospheric gases will now become prevalent outdoors, so it will become more prone to contamination. The weld pool will become more prone to contamination once you weld outside because of the atmospheric gases. Now, basically, hydrogen will attack the molten weld pool that will cause discontinuities and defects such as crack. GMAW has different modes of transfer. The first one is called spray transfer, which has two types, conventional and pulsed. Conventional produces very fine droplets with a higher current setting with a literal spray that turns the wire into droplets, as you can see in the picture. Now, these high deposition rates will limit the application of spray transfer to horizontal positions only. Normally, high deposition rates will not work for positions other than horizontal, because it will get ugly, spatter all over the place, molten weld pool will fall over the welder. The next is the pulse transfer. The pulse transfer varies the current during the process, which enables all position welding because of more control over the weld. It's more similar to SMAW, where the current is like a sinusoidal curve. It can also be used for thinner metals, which cannot be applicable for conventional spray. Now, because pulse current generally or in average has a lower average current, it will be more applicable to thinner metals, unlike the conventional spray, which is more suited to thicker metals because of its high deposition rate. Globular transfer occurs at lower voltage and current but at higher levels than short circuiting. This enables deeper penetration due to the amount of current and heat input. As you can see in the picture below, it's a literal globules that pours out of the filler metal. Short circuiting. It is characterized by crackling sound and can only be used for thin metals or sheet metals. This method is prone to discontinuities because of the inconsistent heat input to the weld. Because of this, AWS D1.1 classified short-circuiting transfer as one of the GMAW processes that cannot be pre-qualified. I mean, you can use it, but you have to do the usual tests like the tensile test, nick break test, bend test in qualifying a weld. You just can't use it in a pre-qualified WPS, meaning you just can't declare it in a pre-qualified WPS and say, oh, we will not test it. So it doesn't work like that for short-circuiting transfer. Here's a summary of the 3 different modes of transfer for GMAW. Remember that the current requirement is increasing from right to left side of the table, meaning short-circuiting is the lowest current among all the transfers. And the conventional spray needs the highest current. Note also for the spray transfer, you can only use argon of at least 80%. If you're using carbon dioxide, it's only for globular transfer. As you can see in the table, it indicates there 100% CO2. Now, since the short-circuiting transfer is for thinner metal applications, it normally requires smaller sized electrodes. Here's the basic nomenclature of GMAW filler rods or electrode rods. The first 2 digits just mean electrode rod, and the next 2 to 3 digits denote the filler rod strength in thousand pounds per square inch or in KSI. The S stands for solid wire as GMAW makes use of a solid wire. This is to distinguish it from other processes like FCAW, which makes use of T, symbol or tubular wire. The last digit denotes the chemical composition. Now, this table shows the most common filler rods for GMAW. I'm not going to run through all of them as you can pause the video anytime. I would like to highlight though a couple of things behind the section of elements here and the shielding gas used. GMAW filler rods have deoxidizing elements, hence there are little to no slag. Thus, it contributes to the increase in productivity that SMAW has that problem. You can see here reactive gases, right? Like carbon dioxide and oxygen. These deoxidizers compensate for that. Now, the deoxidizers are the elements like manganese, silicon, etc. So, basically, the deoxidizers compensate the reactive gases such as oxygen or carbon dioxide for that matter, if used as a shielding gas, because that will react to the molten weld pool or the base metal. Oxygen provides heat input that enables the welding of harder metals. Now, oxygen can be used for higher heat input, but normally or most of the time, it's not used alone. It is normally mixed with other gases such as argon or argon CO2. You notice also that I put in the table here GTAW and GMAW. It's because the filler rods used for both processes are the same. You just get spools of wire meters and meters long for GMAW, while in GTAW, you can use its cutouts basically. Now, the carbon dioxide here is a low-cost shielding gas. That's why it's used almost for every or most of the filler rods mentioned here. So that's it. Or that's the end of the episode, or whatever you want to call this, a tutorial maybe. So if you have any questions, you can email me or post a comment down below. Remember to get your free Udemy course at the video description. Like and subscribe if you find this content helpful. See you on the next one.